The landscape of AI interaction has fundamentally transformed. In 2026, the era of solely relying on prompt engineering has ended, giving way to a more sophisticated discipline, context engineering. This shift addresses the inherent limitations of static prompts in achieving reliable and scalable AI outcomes. Context engineering is the deliberate architecture of the information space an AI model operates within before it generates an output. It is the systematic design, curation, and management of the full information ecosystem surrounding the model. This includes structuring and sequencing data in the context window to enable effective reasoning, moving beyond simple phrasing to architect the machine's entire informational environment. Prompt engineering, once a golden ticket, is no longer sufficient. Early LLMs were brittle, and minor phrasing changes drastically altered outputs. While modern models like Claude 4.6, GPT 5.4 series, and Gemini 3.1 understand intent better, they still face limitations such as information being lost in long contexts, relevant details drowned by noise, and attention sinks. Prompt tweaking cannot reliably solve these systemic issues. The comprehensive context provided to an AI model consists of several crucial components. These include the system prompt, which defines the model's persona and initial instructions, and the user input, which presents the immediate query or task. Additionally, memory systems store ongoing conversational history, external tools offer dynamic capabilities, and retrieved knowledge provides domain-specific information, all contributing to a richer operational environment. Retrieval-Augmented Generation, or RAG, is now a cornerstone of enterprise AI features. It dynamically fetches relevant information from external knowledge bases to ground the model's reasoning, mitigating hallucinations. Modern retrieval techniques move beyond naive chunking, incorporating advanced methods like re-ranking, deduplication, and knowledge graph integration to ensure high-precision, contextually relevant data is presented to the LLM. The Model Context Protocol, or MCP, defines how AI models integrate and interact with external resources. It acts as a standardized interface, allowing models to leverage databases, APIs, and other computational tools. This external tool integration enables models to perform actions beyond their inherent generative capabilities, enriching the context dynamically with real-time data or specific functionalities, thereby expanding their operational scope. Tool calling is a critical mechanism where AI agents dynamically select and execute appropriate external tools to complete tasks. This process allows for sophisticated, multi-step reasoning by assembling context on the fly. For instance, an agent might call a database tool to retrieve specific data, then a calculation tool, integrating the results into the ongoing context before generating a final response, enabling complex problem solving. Effective context engineering relies on robust memory systems. Short-term memory retains immediate conversational history, while long-term memory stores user profiles and historical decisions. Episodic memory captures specific past interactions and their outcomes, enabling learning from feedback. Semantic memory incorporates generalized knowledge and relationships, allowing the AI to maintain state, adapt over time, and apply learned behaviors across diverse scenarios. Managing the context window efficiently is paramount due to token budget constraints, even with windows now stretching to millions of tokens. Models often struggle with the lost-in-the-middle problem, where information buried deep in long contexts is overlooked. Context compression techniques, such as summarization, irrelevant information filtering, and adaptive chunking, are employed to maximize the signal-to-noise ratio, ensuring critical data remains salient. Multimodal context expands an AI's understanding beyond just text. By integrating diverse data types, including images, audio, and video, models gain a richer, more comprehensive perception of the environment and user intent. This allows for tasks like analyzing visual cues in a video alongside spoken instructions or interpreting charts within a document, leading to more nuanced and accurate responses in complex real-world scenarios. Agentic workflows and multi-step reasoning are foundational to sophisticated AI systems. Instead of single-shot interactions, agents break down complex problems into a series of interconnected steps. Each step might involve internal deliberation, tool use, or external data retrieval, with the context dynamically evolving at each stage. This iterative process enables robust problem solving, moving from broad goals to specific, actionable plans. In multi-agent systems, context sharing and coordination are essential for collaborative task execution. Agents must effectively communicate and share relevant contextual information, such as intermediate results, discovered facts, or strategic plans, to avoid redundancy and ensure alignment. This requires sophisticated protocols for managing shared knowledge states and resolving conflicts, enabling seamless collaboration on complex, distributed tasks. Context security is a critical concern, addressing vulnerabilities like prompt injection, where malicious input attempts to override system instructions. Retrieval poisoning involves manipulating external knowledge bases to feed incorrect or harmful information. Robust access control mechanisms are necessary to govern what data and tools an AI can access, protecting sensitive information and maintaining the integrity of the context. Context observability, tracing, and evaluation, known as evals, provide essential insights into AI system behavior. Observability tools allow developers to monitor the flow of information within the context window, while tracing tracks the execution path of agents and tool calls. Comprehensive evaluation frameworks assess model outputs against desired criteria, identifying where context is effectively utilized or where it leads to errors. Automated context optimization and agentic context engineering, or AC, represent the next frontier. These advanced approaches involve AI systems autonomously refining their own context. AC utilizes metaprompting, where AI generates prompts for other AI, and recursive systems that critique and refine their outputs. This leads to self-optimizing architectures that dynamically adapt communication strategies based on real-time feedback and performance. Real-world enterprise applications of context engineering are now prevalent. From advanced customer service agents that retrieve specific product manuals and user histories, to sophisticated data analysis tools that integrate real-time market data with internal reports, context engineering underpins reliable, scalable AI features. It drives systems that personalize user experiences and automate complex business processes across diverse industries. The future of context engineering points towards increasingly intelligent and autonomous AI systems. As models become more adept at processing intricate contexts and leveraging diverse data, the emphasis will shift further from static prompts to dynamic, self-managing informational environments. Continuous advancements in multimodal integration, memory systems, and automated optimization will unlock unprecedented levels of AI capability and adaptability. The evolution from prompt engineering to context engineering marks a fundamental shift in AI development. It acknowledges that effective AI interaction depends not merely on phrasing questions, but on architecting the entire informational world an AI perceives. This discipline is paramount for building reliable, adaptable, and scalable AI systems that can truly understand intent and perform complex tasks in real-world scenarios.